say we have an object that is neutral. It's got an equal number of positives and negatives, of course. 4 and 4, or 10 million and 10 million, doesn't matter. We bring another object nearby that's charged. We'll make this one a negative charge, and we'll bring it nearby up top here. It doesn't really matter where it is, though. We learned that yesterday, right? Tell me what's going to happen to the protons in this neutral object, Jesse? They're going to stay where they are. Tell me what's going to happen to the electrons. Is your hand up, Sadie? Yeah, they're going to be pushed to the bottom because they're repelled by this negatively charged object, right? That goes back to that second law of electrostatics, which says that like charges are going to repel each other. So these negatives are going to go to the bottom. Not necessarily all of them, but lots of them will go to the bottom. So maybe it looks something like this. You got a net negative charge down here, and you have, although not all positives up here, you have a net positive charge up here. Although overall, you got to see that the whole thing is neutral, right? Because it's still an equal number of positives and negatives. Now, this negative object up here will attract this neutral object down here. How come? Well, that third law of electrostatics says charged objects attract neutral objects. Yeah, but fundamentally, why do charged objects attract neutral objects? Why does this particular negative attract this particular neutral object? Yep. All right, Connor? Okay. Okay. Listen, this negative clearly is negative. This neutral object is neutral, but the side of it that's closest to the negative object is positive. So you got a negative object up here. You have, although a neutral object down here, the side that's closest is positive. And what do you know about positive and negative? They attract each other. So we get this negative object attracting this neutral object because negative attracts positive. Even though the whole thing isn't positive, the side that's closest is positive. Okay, and now if I made that a negative object, we'd have the same sort of effect here. Sorry, a positive object, we'd make that have the same sort of effect here, whereas that would attract a neutral object because the negatives are pushed away, and the side closest to it would be positive, or negative, I should say, which is oppositely charged, the positive charging object. Let me get rid of a few of those circles here now. We see what happens. Let's touch that object with a big object. Maybe it could be the Earth. It could be the Earth, but it could be something else. It could be just some big metal ball or some big ball of aluminum foil or something that's a conductor. Tell me what's going to happen. By the way, does it matter where I put this big object? No. Left side, right side, top, bottom, doesn't matter. What's going to happen to the neutral object now? Yeah, we don't necessarily mean all of them, but lots of them are going to move from that neutral object into this big object right here. This big object is exactly the same thing as what? A ground wire, right? We attach a ground wire that goes into the Earth, we touch it with a big object, it's exactly the same thing. In fact, I'd say this is grounding, even though it's not literally touching the ground. Now, if I take this away, then everything's going to go back to the way it was before. But if I separate these before I move that charging object away, then we're going to be left with a permanently positively charged object there. All right? Let me draw a picture of an electroscope now. Here's my electroscope. Let's say it's neutral again. Looks like this. Let's say I'm going to bring a negatively charged object nearby that electroscope. What's going to happen to the protons? Stay where they are. What's going to happen to the electrons? They get pushed down, right? They get pushed down into the leaves. So we're going to take this guy, this guy, this guy, this guy, and we're going to put them down here. What do you notice about the ball of this electroscope now? What's the charge of that? Yeah, it's positive up here, right? What do you know about the leaves of the electroscope? They're now negatively charged, and as a result of them being negatively charged, what's going to happen to them? They're going to repel each other, or they're going to spread out, right? Now, let's say I attach a ground wire to this, or attach something that's really, really big like I did in the last question. What's going to happen now? Yeah, the electrons don't go down into the leaves anymore. The electrons get as far away from this thing as they can, and it means they go down this way. So if we had some positives down here, we had a bunch of negatives, but then they end up going down into the ground, then everything becomes positive, including the leaves. Now, if I cut this ground wire before I take this charging object away, then what am I left with? The leaves are still going to stay spread apart because they're positively charged, still like charges, but now it's opposite to what it was before. Okay, when I brought the negative nearby and didn't ground it, they were negatively charged. When I bring the negative nearby and I do ground it, then they become positively charged. In either case, they spread apart. They repel each other. Okay? Let's take a look at those three questions we had for homework 8, 9, and 10 on page 523, starting with number 8. It says a negatively charged ebonite rod is brought near a neutral pith ball that's hanging by an insulating thread from a support. Describe what happens before they touch and after they touch. So here's the neutral pith ball, a negatively charged ebonite rod going nearby it. What happens to the protons? We've asked this question a million times, and you guys nail it every time now, right? What happens to the protons? Nothing. Stay where they are. What happens to the electrons? Not all of them, but lots of them are going to go to the left. So we're going to get a separation of charge here, right? Negative and positive. This thing is negative, right? This negative is going to do what to the positive side of this neutral object? It's going to attract it. So we're going to find that before they touch, they're going to attract each other. Now, what happens when they touch? Here's my neutral object with the separation of charge. Here's my negatively charged ebonite rod. It touches. What happens now? Neutral and negative. They won't necessarily balance out because the size and shape is different, but they're going to try to balance out, right? They're both going to become negative, which means that we must have got negatives leaving this thing, this rod, into this. So now we get a bunch of extra negatives in here. Still, it may be balanced out, it may not be balanced out, but they're both going to end up being negatively charged. Now, if I separate them, then it's permanent, right? So before they touch, after they touch. Okay, let's take a look at question number 9. Compare the distribution of charge on a hanging aluminum and glass rod. Let's draw the picture here. Here's the aluminum. Here's the glass. They look exactly the same, except the color that I've drawn was different. I'm going to touch both of them with a negatively charged ebonite rod. What's the difference between these two pictures besides the color? Yep. Yeah, the big difference is one's a conductor, one's not. So what are you going to find in the conductor? Yep. You're going to get more of a transfer. Which way is it going to go, by the way? Is it going to go from negative to neutral or neutral to negative? Negative to neutral. Okay, this becomes more negative, right? Same thing's going to happen a little bit here, right? But it's not going to happen as much here as it happened up here because this is a conductor and this isn't. And conductors allow transfer of charge easier than insulators do. Okay? B, after a small negatively charged metal sphere momentarily touches a larger neutral sphere. What happens here? Negative and neutral, they try to balance out, right? Negative and negative. So the electrons are going to go this way. Do they balance? Probably not in this case because this was a lot bigger. Maybe they become -5 and -2. Maybe they do balance. But we know that they're both going to become negatively charged. Just like yesterday, we talked about the electrostatic air precipitator. The dust particles going through those charged rods, remember? They're not going to balance. Okay, the dust particles aren't going to have as much charge as the rods will, but they'll both become negative when neutral touches negative. All right, and we have question number 10 as well. This one says a negatively charged ebonite rod is held near the knob of an electroscope. Here's our electroscope. Explain what happens to the leaves of the electroscope. Well, they're going to spread apart, right? Because the negatives are pushed down in here. So the leaves are going to become negatively charged. They spread apart. What happens to the leaves of the electroscope if the other side of the knob is now grounded while the rod is still in place? It doesn't matter where we put the grounding wire. Same thing's going to happen. This time the negatives are not going to be pushed down into the leaves. They're going to be pushed down into the ground. So that's going to leave the leaves positive. But they're still going to repel. They repelled before because they were negative, now because they're positive. And C, explain why removing the ground first and then the rod will leave a net charge on the electroscope. Cut this. Why does it remain permanently positively charged? Because the electrons have no way to come back, right? They were pushed down to the ground. They'd like to come back. They miss their home. They're homesick, but they have no way to get back because the bridge has been washed out. Got it?